Good morning, everyone. I, Dr. Miskil Naik, welcome you to the national level webinar Physics of Movement from Quantum Exciton Transport in Photosynthesis to Random Walks of Mice in Epidemics. We have among us eminent scientist Professor Nitant Kenkre, Director of Consortium of America's Distinguished Professor of Physics and Astronomy from the University of New Mexico, and above all, he is alumnus of Dhempe College. I welcome you, sir. We also have amongst us our principal, Professor Vrinda Borkar. We also have Head of Department of Physics, Dhempe College, Dr. Ramu Murthy. Also joined to this webinar are the faculty, scientists, researchers, students from Goa, India and abroad. I welcome all of you. Now I request our principal, Vrinda Borkar, to address the gathering.
Namaskar and welcome. I would say good morning from India side to all those who have joined online to a webinar conducted by Dhempe College. It's my pleasure to welcome all to Dhempe College of Arts and Science in online mode. We are honored to have amongst us an erudite personality, alumnus of our college, and that too of the very first batch of Dhempe College, Professor Nitant Kenkre. Let us welcome him to this online platform. I would a little brief that Dhempe College has completed 60 years of establishment. It was started just 6 months after Goa's liberation. The first college to be started after Goa's liberation, because earlier there were no institutes of higher education except for medical college in Goa. And the very first batch we had Professor Nitant Kenkre. And we are very happy also that a person of this stature was developed. The starting point was Dhempe College. I also welcome the participants from UK, Nigeria, Philippines, Bangladesh, Andaman Nicobar Islands, different states of India, and of course, Goans from academia, management, representatives, and my dear students and staff. Sir, it is honor that a scientist with a vision of interdisciplinary research rather than very specific specialization is amongst us. A fellow of American Physical Society, fellow of American Association for Advancement of Science, founding director of an international research center for interdisciplinary science involving biology and engineering. Now, interdisciplinary India is talking now in the new national education policy. So we expect the people to be interdisciplinary, multidisciplinary, and all. Founding director of Consortium of Americas for Interdisciplinary Science. So besides that, he has got 5 books to his credit. Sir, really, we are honored to have you with us, maybe in online mode. But as I mentioned earlier, I am really happy that this technology has brought us together. Thank you all for joining this webinar. And I hope it is a big success. And the success I felt to start with when I saw the colleagues talking so nicely, and the pleasure on their face, and pleasure, of course, for me and Dhempe College. So thanks a lot, Dr. Mishkil. You can carry forward. Thank you all.
Thank you, ma'am. I call upon Dr. Ramu Murthy to introduce.
ऐकूच नाही मला सांग ना.
Thank you, Dr. Mishkil. A warm welcome to all our participants on this wonderful occasion of the national webinar by a very distinguished and eminent scientist who's known worldwide, Professor Nitant Kenkre. I have the pleasure of briefly of the biodata of our distinguished speaker for today's session. Professor Kenkre was born in 1946 in Goa, and a Portuguese colony in India. He is known by the name of DM Nitant Kenkre. He was the distinguished professor at the University of New Mexico, US. Retired since 2016 and lives in Albuquerque. He founded the Consortium of the Americas for Interdisciplinary Science in 2000. And served for 16 years after his retirement. He has published 270 articles on his original research and supervised the PhD dissertations of 25 graduate students who now occupy leadership positions in India and the industry worldwide. He is a critical physicist primarily in three areas: coherence and cycles, electrons and molecular aggregates, investigations in biology and ecology, in physics, non-linear science, particularly the discrete non-linear sorting equation. In fact, interdisciplinary topic will move in from physics to epidemics during his session today. His published books on these respective topics are memory functions. His published books on the respective topics are memory functions, project operators, and the defect technique, theory of spread of epidemics and movement ecology of animals, and interplay of quantum mechanics and non-linear. Interdisciplinary research contributions to statistical mechanics, granular materials, the theory of material-centric ceramics, and the understanding of energy transfer.
Good morning. Good morning, Professor Lusa. I think he is your colleague, sir. Professor Kenkre, he is your colleague. He has also joined. Lusa Gugilo.
Oh, yes. Hello.
Hello.
Luca, yeah, of course he has. I can see him. Right. I can see him right from the beginning. Yes.
I see. Welcome online to Dhempe College, sir.
Yeah, hello. Yeah, I'm sorry, there was a technical glitch. In 2004, he received the Faculty Research Award, the highest distinction that faculty in his university can receive for creative work, as also an award for his international work. He was elected the Fellow of American Physical Society in 1998 and the Fellow of the American Association for the Advancement of Science in 2005. Most recently, the North American Konkani Association presented him a Lifetime Excellence Award for research in San Jose in June 2022. Notably, his colleagues and students published a Kenkre Festschrift in his honor in the International Journal of Modern Physics in 2022. Career appreciation in the form of a Festschrift is extremely rare in the life of an academic scholar. Welcome once again, Professor Kenkre, and it's a pleasure to have you. This morning for this national webinar. Over to you, sir. The platform is yours.
So should I start speaking now?
Yes, sir. You may start. Yeah.
Okay. Uh, so thank you very much. My thanks to Professor Borkar for inviting me. When the invitation came, it was a great surprise because it just came out of the blue. And I was, of course, very delighted for two reasons. Not only because the invitation was gracious, but also because I happen to have a very soft corner in my heart for the Dhempe College. And if I have time at the end of the talk, I will tell you about that a little bit. So, as I understand it, I have been asked to tell you about various researches that I have done in my life with the idea that it might stimulate the students who might hear it. Now, if I have interpreted the intention correctly, then you will have a talk as it should be. If not, it may be something of a disappointment. But I am going to, in fact, give you a talk which is not technical by any means, but it is made up of a few stories. These stories have to do with the researches that I have carried out in my life. It's been a long life, fortunately, and there have been many to pick from, and I have chosen 6 such topics, and I'm going to tell you a story about each one of them. So as I said, I would absolutely love to tell you about the technicalities, but I'm assuming that is not what you want. And at the end, I hope you will let me say something that I feel about Dhempe College and my teachers from that time. And then, of course, you can ask any questions if you want. So this is my conception of what it is that I am given the task of doing. So the title of the talk, as you know, is Physics of Movement. So I want to tell you what physics is, what movement is and why we might study movement. And we will study movement at various levels of nature, from the very, very tiny to the rather large. Tiny means things like electrons and atoms, and large could be, of course, galaxies, but I don't understand much about galaxies. So I will stop at the motion of animals, mice, in fact. So I will tell you about lots of things. As I said, I have chosen 6 items, and I will tell you about them one after the other in a way that presumably will introduce you to many different aspects of what a research physicist in the universities does if he's a theoretical physicist. Now, physics, the best way of sort of thinking about physics is that it is our way, quantitative way of reacting to our perceptions outside. And what this means is that suppose that you are watching a sunset, one of those fabulous sunsets that I miss from Goa. If you watch a sunset, if you're a poet, you might burst into song. But if you're a physicist, you might pull out from your pocket a thermometer and measure the temperature of the radiation coming from the sun, or a spectrometer if you have one, and resolve the radiation into frequencies. And measurement, that means convert it into numbers and try to see if there is a system that you can impose on what it is that you see. Movement, of course, you know what movement means. It is changes in position. And of course, it is one of the many things that you can study in physics. However, movement is something very special in physics. And this you know if you have read about Isaac Newton. When Isaac Newton looked at physics, he did in a very special way. He placed movement at the center of all physics and try to understand everything in terms of movement or the motion. For example, you know that, if you see people moving around, cars moving around, that's movement. Of course, planets circling, that's movement. But you might think sound is not movement. And yet, I'm sure, that sound can be understood completely in terms of the motion of layers of air and of the membrane in your ear. Not only something like sound, but Newton thought of even light in terms of what he called the corpuscular theory of light. He thought of little corpuscles, and now they have taken the form of photons and so on. But he tried to understand even refraction in terms of forces on these corpuscles. So the point is that physics, the way that it is set up with motion or movement in the center of it philosophically. And this is the reason we are interested in studying physics of movement. I'm going to talk to you about the movement of excitons, the movement of electrons, the movement of something that is about 2,000 times larger, which is atoms, then the movement of something much larger than that, like a particle of sand, and then something that is even bigger than that, a whole animal. So this is what we are now, what is in store for you as we talk about these various things. Now, I was trained in the field called statistical mechanics. What statistical means is that if you have many, 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 many of them, by many, we are not talking of thousands, lakhs and crores and so on, but we are talking of zillions. Now, zillion is not a number, as you know, but what it means is if you have 25 zeros in front of one, 10 to the 25, that is the type of number of particles that are in systems that we study when we study through statistical mechanics. And we study quantum mechanics if we need to, we study classical mechanics if we need to, and this is what we do. And this subject, statistical mechanics, in which I am trained, is like a language, so it allows you to approach different aspects of science. And this is why interdisciplinary, as Professor Borker said, she mentioned this word, and this is something that I'm going to stress in my stories that I'm going to tell you. So this is going to allow me to tell you about exercises that I have worked out, which are important to chemistry, to biology, to material sciences, to engineering, and even to ecologies. So it's going to be sort of, how shall I say, very wide in this regard, and I hope entertaining and instructive. So let me start with chemistry. Pretend that you've got a molecule, you're grabbing onto a molecule, and suppose you zap it with light. It will acquire energy, and then as it gives off this energy to its surroundings, this molecule may start vibrating. And one of the first projects that I'm going to tell you about is the study of the vibrational relaxation of molecules. So a molecule can consist of many, many atoms. And the situation, if you want to visualize it, is like if you had a mass that is attached via a spring to a point, and if it suddenly is vibrating like that, how it slowly cools off and relaxes. This is a very important subject that, in fact, my first PhD student by the name of Seshadri, he was Indian, he and I worked out a theory of luminescence while there is vibrational relaxation. A number of years later, so actually this thing that I told you happened in 1975 or so. And then many, many years later in the 90s, I was for a sabbatical in Stanford in the chemistry department. And there is a brilliant man there, an experimentalist, who does experiments on vibrational relaxation. And we worked out a theory of polyatomic molecules in liquids, and their relaxation presents lots of interesting problems. And you are interested not only in relaxation, but in anti-relaxation. What does anti-relaxation mean? He studied, for instance, how the opposite steps can be taken and that you can achieve an explosion. Now, I'm never interested in explosions, he is, but this is something that we studied together, the mechanisms for all of this. Now, this topic, there are many things that we could discuss about this topic, but I'm going to only be satisfied with this little brief description of an application of our statistical mechanical methods to chemistry and move on, since the time is limited, to give you an example from biology. This is something that interested. So this is my second topic. About biology, I'm going to talk to you about photosynthesis. Now, what is photosynthesis? We all need to eat, and some of us are vegetarians and some of us are non-vegetarians. And you know that those of us who are vegetarians eat plants, and those of us who are non-vegetarians eat plants, but sometimes eat animals that eat the plants, for instance, among other things. So what happens is that eventually the nutrition that we need to remain alive comes from plants. And these plants, as you doubtless know, use the process of photosynthesis to manufacture this nutrition that we need. So it's very important that if we just finish off all the plants that are in this world, then we will get in trouble. So it has been thought for many years, it particularly happened around the time that I had started my research career, that people used to think that we will finish off all the nutrition and then it is necessary that we know how to make photosynthetic machines. Therefore, we must understand the process of photosynthesis. Whether or not to make the machines, of course, we should understand the process of photosynthesis. Now, in photosynthesis, what happens is that these leaves of a plant absorb sunlight and cook, so to say, the carbon dioxide and the water that they get into sugar. So this is the idea, as you doubtless know. What you perhaps may not know is that it consists of the process of absorption of light, the chemical processes that make the food, but there is a process in the middle, and that is the one that you and I will talk about now. This process in the middle is that after the light is absorbed, you form an exciton. And Vivek, if you're listening, this is the exciton, this is the excited state, and this is the excited state of a molecule. As one molecule de-excites and the other excites electronically, you say that the exciton has moved from one state to the other, and it is this motion towards the reaction center where the cooking is done, that is the important process that we were interested in. And there were many, many mysterious questions about this process. People didn't know whether this motion happens cold or hot. What does that mean? I just finished telling you about relaxation. So does relaxation of a molecule occur first, and then this exciton or the excited state moves? Or does it happen during, or does it happen after? How does it happen? Was a big question that challenged people. There was another even more fundamental question, and that is whether this exciton or the excited state moves like a wave or moves like a random walker. Now, what does random walker mean? Something that jumps and jumps and jumps and jumps in different ways, whereas the wave-like motion is like an arrow shot from the bow. So this was very important, and it was something that people did not know how to study. They did not know how to even approach theoretically, and this is a problem that we solved. So this was a very important process that occupied me and my friends, sometimes my students, sometimes my collaborators. Over a period of many, many years, we resolved it. We worked out the theory that is then used in photosynthesis and in other allied fields. And this was a major part. And this is an example of how we applied our know-how to biology. This led to lots of things. For instance, when this happened and people accepted the theory, there were, of course, always struggles in the community about a new theory. But when they accepted it, they started inviting me to what was at that time Czechoslovakia, where they used to have every 2 years a seminar, a conference. And I got an opportunity to see the country both before and after the change that occurred in nearby Soviet Union. So it was something that was very nice to be able to travel. So this is another thing that I want to tell people who want to know about the life of an academic person. We get lots and lots of opportunities to travel the world over. And nobody more than my ex-student Luca Giorgioli, who is also listening, who is here, who goes everywhere all the time. In any case, at that time, the work that I did on this sort of exciton motion resulted in a book that they asked me to write, which I published in the 1980s. And I want to show it to you so that you get an idea, and there is a sort of welcome interruption in my stories. So this was published in 1980s, and it is on exciton dynamics, as you can see, in molecular crystals and aggregates. And there is a very recent book with that and many other things that I published just a couple of years ago. And this is the other book, also by Springer. It has got this exciton dynamics and other kinds of stories inside. Now, you see, what I have told you has a process of moving and a process of something happening. This kind of situation occurs in many, many, many situations in all kinds of science. It has a name. It is called reaction diffusion. That means diffusion and then reaction, moving and something happening. And this is something that I have spent a lot of my life on understanding in many different contexts, as you will hear. Not only when that moving thing is something like an exciton, and the reaction is something like the reaction to make food, but as you will hear towards the end of the talk, of the moving object being mice, one of them infected, a mouse that is infected, and a mouse that is not infected. And when they meet, they fight and transmit infection. So there is a diffusion and then a reaction. And this whole thing of reaction diffusion is something very important to understand. And many of my students have worked on this with me and by themselves. And for instance, there was at the beginning a Chinese student by the name of Wong, then a very clever American student by the name of Paul Paris, Luca Giorgioli, he comes from Italy, now works in Britain. He also has worked on this. Ziya Kalai has worked on this from Turkey. So we have done a lot of these things in different contexts when something moves and then something happens, reaction, diffusion. In fact, within physics, in the field of molecular crystals, this was something that's very important, in which you have a crystal like anthracene. And what you do is that you want to know how the excited states that I just talked to you about, these excitons, how they move in these crystals. So what they do is that the experimentalists take something else like tetracene and sprinkle it throughout the crystal. And therefore, how the excitation moves inside is detected experimentally. I spent oodles of my life, I mean, lots and lots of my years in trying to study this in close proximity with experimentalists from Germany and experimentalists, particularly in Germany, from Stuttgart and from Düsseldorf. And we worked on various aspects of it. So this was something very, very, very important. And these things together, starting with photosynthesis, the molecular crystals, generally the transport of excitons is one major activity that I wanted to tell you about. There is something else which is similar, and that is in these crystals, like molecular crystals, if what is moving is not an excitation, but an electron, or, believe it or not, an absence of an electron. The absence of an electron is called a hole, and an electron or a hole moving in a molecular crystal is something quite important, and we were stimulated to learn about it and to do research on it because of my consulting connections with the Xerox research laboratories. You know, photocopying machines require detailed knowledge about the motion of these charges inside. They are photo-injected charges. And this occupied me, and this is another story yet. There was a student of mine by the name of John Anderson. He worked with me. He wrote a thesis on this sort of stuff. And we in fact solved a puzzle. And the sort of puzzle that was there was the temperature dependence of the mobility inside a crystal of this sort. Now, this is connected with an entirely new, large, and exciting field called the motion of polarons, which I would love to tell you about, but life is short, and I can't tell you everything because you will probably throw me out if I talk for too long. And therefore it is that I'm not going to tell you about the polarons. All I will tell you that there is a whole book. I mean, there is an enormous number of my collaborators and I who worked on this. And there is a whole book that I finally, a year ago, wrote. And this book is the one that I'm showing you. It's called The Interplay of Quantum Mechanics and Nonlinearity. And this talks about these polarons. And this is yet another story. Now, I have told you about vibrational relaxation and chemistry. I have told you about biology, photosynthesis, and the exciton motion. And I've told you about electron motion and just hinted at these polarons and this interplay stuff that I have just mentioned. I've told you the book about. I'm now going to enter into something, new story, a bigger object. And this has to do with the fact that when I went to the University of New Mexico, they made me a member of, I came in contact with lots of engineers and material scientists. And the story I'm going to tell you is about microwave heating. I'm assuming that you do heat things in microwave ovens. Why do I say this? I say this because when I was in India, there were no microwave ovens, I know. And therefore, I don't know whether it is something that we normally do in India or not. But I'm going to assume that you're familiar enough to know, first, that if you want to heat up your food, you can put this food in the microwave oven, number one. And second, that you should not put the spoon inside the microwave. I am assuming that you know this, and you probably want to know why. The reason that you can put your food inside the microwave oven and heat it is because the water molecules in the food accept microwave through resonance, and that is the way that the heating occurs. And the heating that should not occur in the metallic spoon that you put is because something you want to avoid is because there are too many free electrons inside the metal. And if you excite them, you're going to have an explosive situation. Now, this is the sort of thing that I see here a message, by the way, for me, that Avinash Ashok Gaikwad has raised a hand. May I request that you keep the questions to the end? Is that okay? That would be good, because otherwise, in my advanced age, I might tend to forget what I was going to say, and then it would be awful. So if it is possible at all, please keep the questions to the end, and then please ask them, because I'm very interested in hearing. Now I see another one. Avinash Ashok Gaikwad has raised a hand. Is there something I'm supposed to do? Can someone say something to me? Is it necessary that I interrupt the
So you
talk?
continue, and all the questions will take. No, not at
Okay.
all, sir. You continue with your talk, and questions we are taking at the last. And when anybody raises the hand, that will be taken in that sequence.
Okay, perfect. So
Yeah.
just needed to know, and so okay, fine. So the what I was trying to tell you is about the microwaves. Now, what happened around the time that I went to New Mexico, joined the University of New Mexico, is people used to talk about microwave heating that people had discovered of ceramic materials. And this is something that was enough to blow the mind, because ceramic materials do not have free charges, and ceramic materials certainly do not have water molecules. And therefore, there was the question of how come they are heating. And the point is that this heating was used in microwave sintering, and it was necessary to solve this puzzle. There was an even bigger puzzle than simply heating, and this puzzle was something called thermal runaway. I'll tell you what thermal runaway is. If you take a ceramic material of sorts and you hit it through microwaves in the way that I have said, then people observed something really odd, that on a matter of seconds or minutes for some materials, the heating was mild, and then suddenly it became very strong. This is called thermal runaway, because then it gets very, very hot, and you wanted to understand why it is slow at the beginning and suddenly a lot later on. I constructed the theory of these also on the basis of motion, and I was successful in solving this, and we had a wonderful collaboration of various people. There were people who dealt with microwaves at Los Alamos. There was a fantastic postdoc that I had from Poland. His name was Marek Kusz. And there was once Paul Paris, an ex-student of mine, had come and he worked out another theory of thermal runaway. And these theories, the ones that I work primarily in, were based on an idea which I will try to tell you very briefly right now. Although ceramics do not have charges, what happens, because when the atoms in the ceramic material move about because of temperature fluctuations, you produce ions. That means atoms with charges on them. And when they move, you have vacancies. And now the atoms and the vacancies, one charge positively and one charge negatively, form electric dipoles. And the most interesting thing is, and listen to this carefully, although I cannot tell you all the details with mathematics, the concept is very interesting and very simple. When you have got charges or dipoles which are constrained to closed spaces, then they do not absorb much. This is very easy to show. But if they are free, they absorb a lot. Now look at what happens. When you have got constrained charges, when you heat, they absorb not too much. But when they absorb, they can get out of the confinement. So the absorption not only produces absorption itself, but also freeing of these. Now, when they are free, they absorb a much, much more. And therefore, there is a feedback process. And this feedback produces that thermal runaway that I told you about. What is that thermal runaway? That you heat slowly at first and then suddenly explosively. So I hope that these examples that I'm giving you, which are coming from different levels of science, different fields, but different levels, they tell you how it is that the motion of these various different objects actually cause, exactly as Newton had envisaged when he placed mechanics in the center of all physics, how all of this happens. So that is one example, moving towards macroscopic physics, normal scale physics rather than atomic scale, that I have given you. Now I'm going to tell you the next item. And don't worry, I only have 2 more items to tell you, and then I will bring this to a close. So the next item that I want to tell you about is the motion dynamics of sand, of granular materials. This is something that I began to study because of the interaction with friends, scientists, colleagues at the Sandia National Laboratories, here also in Albuquerque, particularly a man called Alan Hurd. So what happened is that there were many different problems to do with sand. You may not realize why sand is important or granular matter is important and why it is difficult, but I'm going to tell you now. You know, I mean, you are not, in Goa, we do not have snow, as far as I know, but here we have snow. And so you know that on the mountains, there are these avalanches of snow, and that to know how avalanches occur is something very important, obviously, for human relevance. And sandstorms is also, which can happen anywhere in the desert and so on, is also very important. But commercially, you know that one of the most rich, wealthy industries is the pharmaceutical industry. And if you want to know how to manage pills, you must know how to manage sand, which means granular materials, right? I mean, what are we talking about? We are talking about anything like a powder or sand or snow or anything of this kind that is made up of many, many particles. Now, let me ask you a question. What do you think? Would you call sand a solid or a liquid or a gas? You see, if you take sand and just put it down, then it stays. Therefore, you would call it a solid. You take sand and you pour it in a beaker and it takes the shape of the beaker. Now you would call it a liquid. Suppose that in a drum or something like that, you move it, shake it very hard. It flies like a gas. How do we study it? You will be amazed to know that in this century, people have, even now, people have absolutely no idea of how sand behaves. There were two very important problems that I tackled with the help of my students and with the help of my colleagues in sand dynamics, that means granular science. One had to do with something that I will call static, and one had to do something that is dynamic. What is the static thing? You know, if you want to make a car, you have to make an engine block. If you have to make an engine block, you have to take materials, and then from there you put it in the oven and so on and make the engine block. But you know what happens? Unless you know how, when you compact sand or a granular material, how really the stress inside distributes throughout, then you will produce an engine block. If you don't know how to do it properly, you'll produce an engine block that will crack. So it is very important for such industries to know what happens when you take sand and compact it, how the stress distributes. This is a remarkably difficult problem that we solved on the basis of an idea that I developed having to do with motion that is microscopically wave-like and then becomes diffusive further on. And this is a beautiful, very pretty mathematical idea of replacing space, time by space. So what happens in time in the equations that we study is translated into what happens in space in a granular compact, and you are able then to use what you have learned in one field of physics into completely a different one. And this is interdisciplinary work at its best, so to say, at its cutest, if nothing else. So this is one of the examples that was very important to people at Sandia, stress distribution. There were a couple of students who did their thesis work on this with me. And then there was the other kind, which has to do with the dynamics of sound. And dynamics of sound means, you know, you might have seen cylinders on whenever road work is carried out. There are cylinders in which there is materials, granular materials, that is moving about. Now, please think along with me. If you have a cylinder and you put inside, okay, this is an empty cylinder in which you put inside sand, granular material, and you start rotating it, what will happen? The granular material, if you are rotating it slowly, then it will move in a way which is a jerky fashion, And if you move it very fast, then of course the sand will fly. But if you don't do very fast and very slow, if you have an intermediate way in which you maintain, then you know that there will be a curve that will show the surface of the sand. The big question that we set ourselves to solve is, can we calculate or predict the surface, that means the equation to the curve, the geometrical equation to the curve that shows the surface of the sand. And I developed a theory which I used to call one-dimensional granular hydrodynamics. With the help of that, I was able to get this sort of a curve and compare it to experiment. And it is based then, the parameters of the curve, on the friction between the particles and the size of the particles, and of course the nature of the particles. But you can do this, and this was something that was quite a success and quite good and useful to my collaborators in the fields in which we were working on. So these are two examples of this weird and strange macroscopic example of motion that I have told you, the static one that has to do with the distribution, and the dynamic one that has to do with this surface situation. And now I come to the final example, the sixth example. So one of the things I want to do is, as soon as I'm done telling you about this last example, which by itself is fascinating, as you will see, I want to show you, I hope I succeed in showing you some document that I have got on my laptop here, like a presentation. And if I'm able to, it will punctuate our talk by you are seeing some pictures, and then this will allow you you to fix in your mind what it is that I have talked to. But now I have arrived at the sixth and the final topic that I'm going to tell you about. I told you that my story is split into these parts. Of course, then after that, you will allow me to just spend a minute on my thoughts about Dhempe College. But let me tell you now the last one. And I see another question, but I should be ignoring these questions, right? Yes, because they will be asked of me at the end. So what I want to tell you now is the final topic is the application of physics methods to ecology. That means to something as distant from physics as the spread of epidemics. So it's not COVID that I'm interested in, although, now everybody's, or has been until recently, interested in COVID. I'm talking to you about work that I have been involved in for 25 years. And at the beginning, you heard about Luca Giugioli, who used to be a student of mine. And he, in fact, wrote a book with me. And here is the book. Look at how, what it looks like. And it is the theory of the spread of epidemics. That other fellow, that's not me, is Luca Giugioli. And this is a whole book that Cambridge University Press wanted me to write. And I asked Luca if he would join me, and we wrote it, and that also was published recently. So let me tell you about the sort of things that are there inside. The idea is like this. You are worried about an epidemic spread, and I will talk to you about the simplest epidemic possible to think about. And this is an epidemic that may not be of importance to you in Goa, but it's very important here in New Mexico. It is called hantavirus. It is an epidemic that is spread by mice There are infected mice and not infected mice that are called susceptible mice. And what happens is these mice move on the terrain. Remember the word move again. They move on the terrain, on the landscape. And when they meet, when they come close to each other, they fight. And if they fight, they transmit infection because they are in the neighborhood of each other. And this is the way, that is the basic problem. And our idea, and this was an idea that we developed, I mean, the basic similar ideas many people have thought of, but the idea that we developed for hantavirus, and this we meant a colleague of mine called Guillermo Abramson from Argentina. He had visited me and we worked on it after we had listened to some of the biologists, some of the ecologists who had been working on these situations for years and years, and they had discovered hantavirus in New Mexico. And the idea that we had was to think of this like molecules of a gas. If molecules of a gas, as they are moving about, they collide against one another, they can transmit to one another energy and sometimes, various other sorts of the angular momentum and things of that sort. The idea was to consider in a very similar vein that infected mice, like the molecules of the gas, and others that are not infected, they might collide and transmit infection. This is a beautiful story. And among others, I mean, there are many people, many of my students who have been involved in this. One of them who has in fact taken this in his own career and done great things is Luca Giugioli, who it's so nice that he is here listening at the moment. He has worked on bats and foxes and all kinds of things of this sort. But remember that a few minutes ago, I talked to you about the phrase reaction diffusion. This is also reaction diffusion. The mice are moving about like random walkers. They meet and something happens. This something for us now is, for instance, the transmission of infection. This is a beautiful subject. And this itself is something that I could talk to you about for long time, but we don't have the time for it. I want to bring this to a close. So I'm going to tell you that one of the fascinating things that occurred, and Luca Giugioli was one of the collaborators at that time. He was a student of mine at that time doing his PhD on these things. And this Guillermo Abramson, for instance, we were, along with the experimentalists, the biologists who observed these things, were interested in applying this theory that Guillermo and I had developed. And what happened is that we found that these mice had one property that we had ignored, everybody had ignored. This very important property is that these mice like to be close to their homes for shelter. Now, if they like to be close to their homes, these things that are moving are not like the molecules of a gas. They are not random walkers that move and random walk freely. But what they are, listen to the phrase that I'm going to use, what they are is tethered random walkers. Did you get that word? Tethered, tether. That means random walkers that are on a leash where the other, this is an elastic leash if you like, but the other end is tied to the home. What I mean, there is no actual leash. What I mean is that they tend to be close to each other. This required a completely new theory. And this is something that the new theory we worked out. I worked it out completely. It was a lot of fun to work it out all by myself. in one dimension. This is something that we do often in theoretical physics. We solve a problem in one dimension because it's easier to do so. I solved it, and then another student of mine, Satomi Sugaya is her name, she extended it to higher dimensions, the actual dimensions that in which mice really move, and we found beautiful new effects. And this is something that is in the book that Luca and I put together. Now, there are also other things that Luca himself did after he left my group. And these have to do with cooperative motion of animals. Now, to understand what cooperative motion of animals means, you've looked up in the sky and you've seen birds moving like a flock. Now, flock moving of birds happens because the birds have attractive interactions between them. Luca is an expert on the opposite. He is interested often when animals repel animals by repulsive interactions. And this they do by leaving stuff, waste products, for instance. As you doubtless know, that sometimes animals will leave waste products to stop others from coming into their territories. And this is something that he has evolved very wonderful theories and so on. And so this goes on. This is fascinating stuff. This is reaction diffusion. And we have also applied it with a friend of mine, also from Argentina, called Marcelo Cooperman. I applied some of these things to bacteria in a petri dish. So just think, I mean, we were talking about interdisciplinary stuff. You can go from level to level, from field to field, and apply these ideas, move and borrow ideas from one and apply to the other, and have lots of fun. And this is what we did in this ecology. And the last 25 years, I think, of my life have been spent primarily in this sort of problems, even though there has been a lot more. I mean, one cannot draw oneself away from the quantum mechanical, from Polaron dynamics, and so on. Okay, so I have told you now about the 6 projects that I wanted to tell you. Now I want to show you visually a couple of things. So I think that present my entire screen. So I am trying to, okay, please someone tell me whether do you see, what do you see what is in here?
So there is a arrow which is there. Click over there.
Yeah, I clicked the arrow. Do you see now?
Then no, sir.
You don't. I see.
No, sir.
So let me.
So go to arrow.
I see the arrow, and it says present now.
Present your entire screen. And then highlight that screen, sir. Or select that screen which you want to share.
Do you see it now?
Then press the button share. Yes, sir. We can see.
You can see. So are you seeing? Please, someone tell me. Are you seeing the
Yes.
talk in outline?
Yes, sir. Yes, sir.
Oh, good. So this is very nice. So I will be able to now just show you a couple of things I want to show you so that you do not forget everything that I have talked to you. So we talked about the physics of movement, and the subtitle, let's see, the subtitle that I gave was for quantum exciton transport and photosynthesis to random walks in mice and epidemics. Please notice that as the first topic, we talked about vibrational relaxation that allowed us to talk about chemistry. And about that, I wanted to show you. Yes. This is the only one for which I want to show you. Why don't I don't see? Anyway, what I want to show you, I am not able to see myself. Ah, that's right. Can you see something that shows vibrational relaxation chemistry and the names of some people?
Yes, sir. Yes, sir.
Okay. So I
Yes,
just
sir. We
wanted
can
to
see
tell
it.
you. Okay, good. Then this is just to tell you that this was the student, the first student that I ever had as my PhD student, and we worked on the interplay of luminescence and relaxation. This is something that I had told you about at the beginning. The experimentalist at Stanford is Mike Fair. With him and his student, I worked out a theory of vibrational. This is a sort of a comprehensive theory, which is very interesting. And this sort of thing continued with my last two students, Matt Chase and Anastasia Iridis, who worked on the quantum mechanical aspects of vibrational relaxation. So this is something I wanted to show you to fix in your mind vibrational relaxation. Now about photosynthesis, I am not going to show you anything more except a picture. No, not the book. You have seen the book. Ah, this is the picture I wanted to show you. Can you see the, just so that
Yes,
you
sir.
do not forget, yes, just so that you do not forget, I want you to think of the leaf. Think of the Frankel excitons as the moving objects, and the process is the photosynthesis in leaves. And then what I want to tell you is the granular stuff that I told you. I told you about two big problems, and they are listed here as dynamics and statics. What had happened in the statics, I didn't have time to tell you in great detail, but what had happened in statics is that if you take a compact and you look at the stress distribution when you press something from the top, then it is almost as if something was traveling down a wave that is reflected from the walls. And with this concept, I was able to make a theory that explains experiment. And the other thing was the dynamics. This is the cylinder that I had told you where you are rotating it in this fashion. And please understand that in terms of my theory, we were able to compute this curve analytically and quasi-analytically, quasi-numerically, but we were able to compute this curve in terms of friction, size of the particles, and so on. Now, what I want to tell you is what is it that we end up doing when we write papers? And the second thing that I want to tell you is that we write books, and we have been writing a number of books. And an ex-student of mine, that Satomi Sugaya, who had worked on epidemics, helped me in producing a display of all the books that I have written, that you might find it amusing to see. So you should ignore these books because they are not about physics. These are the books. I just showed you the cover of the Epidemics, the one that Luca and I wrote. I have shown you these Polaron stuff, quantum mechanics interplay. I showed you these two at the beginning at the excitons. And this is also a fascinating book that I co-edited with Katja Lindenberg. And this is on the methods of statistical mechanics. So this is the sort of thing we end up doing when we are in academics. We write books, we go to conferences, we talk to people. But what is to me has always been most important and most pleasure giving is the working with my students. You speak with your students, you help them grow up into scientists, and they have all made me very happy by turning into fantastic professors and scientists of all kinds. Okay, I am now going to finish my talk within 2 minutes by telling you about Dhempe College. Professor Borker has told you already that not only am I an alumnus of Dhempe College, but I come from the first batch. We started it all, so to say, and I have such tremendously fond memories and a feeling of great gratitude towards my teachers that I want to tell you passingly about it. I want to tell you, for instance, that I would not have come into physics, I would not have come into mathematical sciences, because my interest was always in literature before. And the one man who was responsible for converting me, so to say, and coming into mathematics or mathematical sciences is a person who is no more now, but whom I remember fondly and I'm grateful for, is Professor Joe Menezes. He is the man who is largely responsible for my doing mathematics and understanding how pretty it can be. And I want to talk to you. I mean, I also typically do not like to read things with you, but I'm going to. So do you see this remembering my Dhempe College teachers?
Yes, sir.
Okay.
We can
So
see.
I want to tell you, this will just take a minute, but this is very important to me. This was an article that I wrote probably 20 or 30 years ago. And it was an article that it spoke about what Professor Menezes did. And so it says, the stranger's name was Joe Menezes. Then I want to tell you, Dhempe College gave my friends and me many other dedicated teachers. Nat Kearney teaching mathematics in a systematic way, turning corollaries and lemata from foes to friends. Harite converting impossibly difficult concepts in organic chemistry to digestible chunks. Sukhtenkar centering on the mysteries of physics and stopping students from running away from centrifugal forces. Antaum, Vaz, and Lavande, Junior Lavande to be exact, since there was also Senior Lavande, the friendly despot, our beloved principal, whose booming voice in college corridors and NCC fields still reverberates in my ear, and Ashatai and Daliatai. Daliatai was Dalia Joshi. Ashatai is there listening to this talk now. I'm so happy to see that. And Ashatai means she was a friend of the family. She's a friend to me. She's like an older sister to me. And she was Asha Vaidya. I've said here one who could discuss P.G. Woodhouse as well as physics. That is her. And the other who could command and march sternly in parades when not teaching physics. So I'm going to stop here truly and give me a minute while I see that there is a low battery, which I'm going to uh, just connect so that we can continue this. Give me a minute. So I'm going to click on that thing that says stop. So I have clicked stop presenting.
Yeah, it is stopped presenting, sir.
Good. So now I am at your disposal and ready to answer any questions that I know how to answer. Thank you so much again for giving me this opportunity to relive a little bit of my contact with Dhempe College.
Sir,
Thanks.
your talk.
Yes?
Thanks a lot, sir, for accepting our invitation as well. And I think we shall take the questions which are there in the chat box.
So what should I do?
So I'll read out the questions to you.
Okay, please.
This question is from Vivek Montero. He
Okay.
asks, is the motion of excitons in photosynthesis a diffusion motion or something else?
So Vivek, is your question, is the motion of excitons diffusion or something else? Is that the question?
Yes, sir.
Okay.
Yeah, that's right. That's the question.
Yes. So in fact, Vivek, this was the most important question that we had at that time. And what we found out first is that the theory that I developed showed how to ask this question through an experiment. And when you do the experiment, you can find out in a given system whether it is the motion is diffusive or the motion is wave-like, to what extent it is wave-like, and to what extent that has been converted. So this was the million-dollar question, so to say, and this is what we answered. So the answer to your question is, it depends on, of course, on the system and on the temperature. Going to the photosynthesis in leaves, it turns out that in most cases it is diffusive, and in situations like anthracene, under 15 degrees or so, it is not diffusive, it is wave-like. And so you can go in and do specific experiments which we designed, by which you can answer this question for each system at each temperature.
So
Okay.
his second question is,
Yes.
a chain reaction is an example of reaction diffusion.
Please repeat the question. Please repeat the question.
Is a chain reaction is an example of reaction diffusion?
I wouldn't say that. A chain reaction is something different. A chain reaction is, no, the reaction diffusion is something at which you have diffusion and there is a special event, but I mean, it's not that there isn't a special event in a chain reaction, but the point is about the reaction diffusion, the concept is that you try to study about diffusion or about the reaction. Typically, you study about one of these because the two are of widely disparate time scales. This is not necessarily the situation in the chain reaction. So I would not say, I would say that the chain reaction and the reaction diffusion have only the word in common, not the concept.
Thank you, sir. So this is another question from Keshav Kumar. His question is, uh, how do we see the spread of tumor? How do we see
How
the
do we
spread
see
of
what?
tumor invasion? How do we see the spread of tumor invasion, that is metastasis? Metastasis.
How do we see the spread of tumor in
Tumor
metastasis?
invasion. Yeah.
So
So he
I must
further writes, if
confess,
we can further he writes, if we can understand its spread, I think we can have cure for cancer. And he's asking to throw some light on this topic.
so I must confess that I do not know the answer to this question. This is not something that I have ever studied about the spread of tumors in metastasis, and I really have no idea how that happens. So I would think that that's quite outside subjects that I have studied. So I have no idea.
So this question is from our student Harsh Ambankar. He is a biotechnology student. And his question is, from a book, from your book, sir, my question is that in your book, Interplay of Quantum Mechanics and Nonlinearity, how did Schrodinger equation help you to understand the dynamic system?
How does it? How?
From your books, yeah, from your book, that is Interplay of Quantum Mechanics and Nonlinearity, how did Schrodinger equation help you to understand dynamic system?
Okay, so this is the book that you're talking about, and how does it? So there are many situations in which one can study the dynamics. For instance, there are weird things that happen in the mobility of polarons. For instance, there is a question as to whether it is possible for strong electron-phonon interactions to lower the mobility of electrons drastically, so that when you heat up a system, it is possible for the mobility to come down, and whether it is possible for the same kind of interaction to cause the opposite. And this shows the interplay of quantum mechanics and nonlinearity in the book that I'm talking about, that this process occurs as a consequence. This is one example. A completely different example is that of the dynamics of Bose-Einstein condensates. So we studied Bose-Einstein condensates with the help of this nonlinear Schrodinger equation, and it helped us understand how transitions occur in the motion of Bose-Einstein condensates and the tunneling of the condensate. So these are two of the many possible answers that I could give this answer.
If anyone has more questions, to either put it in the chat box or unmute yourself and ask, sir.
So I see a question here whether, oh, it disappeared. There was a question
So
that
this
was on
question, this
Please.
question is from our student, sir, from Roland Pereira. He asks, why does adding more sand on a sand heap increases its height sometimes, but also causes an avalanche at other times?
Please say that again.
Why does adding more sand on a sand heap increases its height sometimes, but also causes an avalanche at other times?
That's an excellent question. This is something that this is a critical phenomenon. You know, it is a little bit like the flavor of the question or the flavor of the situation in physics is like, you know, what happens when you take water and you heat it, its temperature increases. At one point, it turns into steam. So that's a critical phenomenon. The avalanche situation is also like that. You put in more sand, the height just increases, and then suddenly at one point there is a critical phenomenon, and then therefore it is that the avalanche proceeds. So it is in the family of phenomena that are called critical phenomena. And the details of the dynamics is something that I cannot explain to you, of course, here like this, but it is something that can be expressed. But it is a critical phenomena. That is the reason this happens.
So there is another question from Harsh. He asks, do you think quantum ring could help us study more in depth about time travel, dark matter, wormholes, and other space-time entities?
So I must confess that I am a total ignoramus when it comes to these concepts like dark matter. So I have no idea, and I am extremely careful not to speculate about things I do not understand. I'm very religious about it, and therefore I regret to say that I cannot answer this question because I don't know.
So there is another question from Shubham Gawas, and I just read how he has put it. He's asking, can hantavirus theory could be applied to COVID-19 spread?
Okay, so this is a question of
theory. Yeah.
So this is a question, as you can imagine, that has been asked to me over and over again many, many times. And I can tell you that what is best to the final answer is no, unfortunately. But I'll tell you why, so that you understand why it is that we don't go in and do it. The reason is the following. In the case of COVID or COVID-19, the way humans are infecting humans, and therefore what is very important in a society like ours is the pathways through which humans go, where they meet, what they do, and so on. So this falls under the auspices of what might be called network theory, rather than the theory that we have developed for the hantavirus and things of that sort, which is much, much, much simpler because it has to do with random motion of the mice. So when you have got a random motion or a motion that you know for sure, which is of a very simple kind, then you can apply our theory. So that theory, the theory that we applied for the hantavirus, we were also able to apply to the dynamics of bacteria, for instance, but not to something as complex as humans. COVID-19 derives most of its intricacies about connections from network aspects, and that is something that we cannot hope to do in the simple terms that I have talked about. For that, you would need totally different methods.
Thank you, sir. So there is another question from the faculty from Goa University, Dr. Rajesh Hyam. He is asking, is it possible to understand reduction in resistance of material to zero by understanding the interaction between the electrons at low temperature so as to achieve near room temperature superconductivity? I repeat, so again, is it possible to understand the reduction in resistance of materials to zero by understanding the interaction between the electrons at low temperature so as to achieve near room temperature superconductivity?
Yes. So I understand this is a big field of room temperature superconductivity. And for me, it is how shall I say it? It is a different field about which I know only like a layman. So I do know that the things that I have talked to you about polarons are go into a theory which is, for instance, Bardeen, Cooper, and Schrieffer, when they developed their basic theory of superconductivity, they used concepts that are closely allied to the concepts of the polarons, but not directly. And this is something that uh, maybe will be at work in trying to get understand the room temperature behavior. This is something that is becoming quite important. Uh, it began to be important several years ago, but more than this, I cannot say. This almost belongs to the same kind of problem that I don't understand much about, and therefore I would not want to speculate. So I really don't know.
Thank you, sir. Anyone wants to ask any more questions are free to ask. So here there is one question from Rohan Burye. Uh, Here he is saying, how fruitful is career in academy and research compared with industry, and how to excel in research career?
So the first part of your question is how research in industry compares with research in academia, right? And the second one is how to excel in research. Am I right?
Yes, sir.
Okay. So as far as industry versus academics are concerned, the conditions of research are often different in the sense that in academia, you do not have to be as directed by others as you have to be in industry. For instance, those of my colleagues who were in the industry could have also been doing the work on those copying machine stuff that I told you about, the electron transport and so on, which I did being in academia. The big difference was that I didn't have bosses telling me to do this or that, whereas in the industry, you have bosses because the idea of the industry research is directed research. You do not want to dissipate. There's nothing bad about it. That is the characteristic of research in industry. So there is much greater freedom. So I, for instance, in academia, in the middle of doing my research on electron transport, I could have, how shall I say, written poetry or something else, or suddenly decided to work on black holes or something like that. So the freedom is characteristic of research in academia, and directedness is characteristic of research and industry. This, I think, is a succinct answer to the first part of the question. Now, the second one, how to excel in research, that's a very open-ended question. And how to excel in anything? I think one has to love that which one does. One has to never look at it as a task, and just forge ahead. And I mean, if for instance, this was a question put to me by a student, and if I could help the student who is asking the question by telling specifics about what to do, how to read, how to think, I could have done that. But in this kind of an interaction, it's impossible for me to answer that question. So all I would say is, well, I don't know. How to excel is too difficult a question to answer.
Thank you, sir. Are there any more questions? Shubham Gavas has one more question. Is thermo runaway beneficial, and how can we avoid or minimize it? Is thermo runaway beneficial, and how can we avoid or minimize it?
Okay, thermal runaway, right? That is the
Yeah,
question about. Okay.
yeah.
So the question is thermal runaway. Suppose, I mean, very simply said, there is a positive part to it and a dangerous part to it. The positive part to it is that you heat a lot. So suppose that in the first region where it is heating very slowly, it is not enough to do the job that you want, then it is beneficial when it is heats a lot. However, thermal runaway can have and does have sometimes undesirable characteristic because it can get out of control. So it is a little bit like an explosion. It's not an explosion necessarily, but it is a little bit like an explosion. So whatever it is that you want to do to transmit the energy, you can do a lot. That's the good part of it. And the fact that it may be in a very uncontrolled fashion is the bad part of it. I hope that answers the question.
Thank you, sir. So I'd just like to say, Rohan Burye is actually a research student who is doing his research at IIT Goa. That's why he had asked this question to you. He's a research student at IIT Goa, Rohan Burye.
I did not understand what you said. Could you repeat that, please, for me?
Sir, Rohan Burye is a research student at IIT Goa. So that is why he had put that question. Yeah.
I see.
Yeah.
He had put the question regarding research careers.
Oh, I
That is
see.
what she, yeah.
Yeah, I would.
Which you
There
explained.
there is something I want to tell you, which is that while I was showing you various things, I had also prepared, but I forgot to show you my emails. There are two emails. One is the Gmail and the other is the university one. And I'm telling you that if anyone has any kinds of questions, either about my talk or about any other general questions like the ones that I'm hearing now, I would be absolutely delighted to receive questions over the email. So I had actually prepared something that shows the two emails, but please contact me with any kind of question, and I would be very happy to answer.
Shall I share your email, sir, here?
Absolutely.
Okay. vmkenkre@gmail.com. Dr. Mishkil?
Yes, madam.
Okay, there is one more question. What are the effects of external biotic and abiotic factors in virulence and the risk of infection?
So I did not understand this question. Please repeat it or reword it. What are the
Effect of external biotic and abiotic factors on virulence and risk of infection?
Okay, I would think that this question would be for people in infection fields, medical ones or something like that, because as I interpret the question, I don't think it comes in my expertise. So I'm so sorry, but I don't think I have an answer to that question.
Okay, sir, you have given enough time to us. and I'm really happy. And I did not feel that we are online. Actually, I feel as if you are with us, explaining all your success stories, and also I would say your books, your research in a very simple way, which I know the best researcher is the one who gives simple answers for most complicated cases. So, Dr. Mishkil, I think is the time. Okay, that I
Yes,
don't
ma'am.
see any more questions also.
Yes, ma'am. Yeah.
Yeah. Thanks a
So,
lot, sir, for
Yeah.
joining and accepting. Now, let Dr. Mishkil take over.
so
Yeah.
I just
So,
wanted to, before she does, I wanted to respond to what you said by saying that I consider this an opportunity that you have given me to, so to say, be in the environment of the Dhempe College. And to me, it's very valuable. It's no task at all. I am absolutely delighted. I would like to thank you, in fact, for being with you all. That's it.
Thanks, sir.
thank you, sir. So, in your talk, you have emphasized on the motion, that is movement, not only restricted to physics phenomena, but also to other branches of science, that is chemistry, biology, and geology, ecology. So the motion is not only restricted to only to that of the physics. So these laws of motion are also applicable to other branches of science too. So whether it is static motion, dynamic motion, and also you correlated the examples, the mice example, the birds example, and how you were discussing about their random motion and all that. Really, really fascinating story of motion, and the books, your contribution in the form of books which you have come up. I congratulate you, sir, for writing these books, and I hope that I get to read those books also, and then to share my views on those books. So we also have here one of our senior most faculty from Dhempe College, Dr. Antonio Barboza, and I would like him to say a few words.
Okay.
Hello, hello, Professor Kenkre. In fact, you won't know me. You just left this college for engineering after your into science, and I joined. So, but I've heard a lot about you as well as that Vivek Montero, another personality. So it was really nice. I got a nice opportunity to hear you personally. I especially came to hear your the talk in Denver College today. So nice of you, and all the best. And it is really nice to talk about our old students, even though I did not know you personally. Okay?
Likewise, thank you so much for saying these things, and I'm delighted to make your acquaintance.
Now I request our head of department to propose vote of thanks. Feedback form is also, link of the feedback form is put up in the message.
Yeah, thank you, Dr. Miskil. Yes, sir. It's been a wonderful session that we had today, where you spoke about 6 important developments in your long career of 25 years at University of Mexico. And the astounding part of your talk was the beautiful way in which you transform from physics to various other branches of science like chemistry, biology, material science, and that's what made it very, very interesting. So I'm pretty sure that all the participants today, must be extremely happy to have listened to your wonderful talk that you gave, and the way you touched on the aspects of physics of motion, and you correlated them to various other fields of science. Thank you so much, sir. We hope to hear from you in future too, and Yeah, it's been a pleasure. It's been a pleasure seeing you online. It was a wonderful pleasure to see all those very close friends from Goa, who are also so nicely interacting with you. And I'm sure Madam Principal also was very, very pleased. In fact, I mean, I could see it on her face because, she was beaming with, she was beaming with joy when she saw, all your close classmates of those gone by years, who are here to be a part of this wonderful talk that you delivered today. Thank you so much, sir. I also wish to
You are
thank
most welcome.
Thank you, sir. I also wish to thank some of our very senior faculty from, from Goa University, our former Vice Chancellor and ex-director of National Institute of Oceanography, Dr. Satish Shetty, and some of our senior scientists like Dr. Ramesh Kumar, who are all a part of the wonderful audience that we had for your session today, sir. Thank you so much. Thank you, sir.
You're most welcome. The pleasure is mine.
Thank you, sir. Good night.
Good night.
Good night, sir. But before that, we keep our invitation in person to Dhempe College. So I hope you accept
Okay.
our invitation to be in presence. Okay. Visiting Dhempe College and see the new look of Dhempe College. Okay. After many years. Okay. So Goa also has changed a lot. And I think you will enjoy the change in Dhempe College as well as you will be able to meet us all in person. So we have a wish that you should come, and it's not a very big difficult thing. It just takes 24 hours to reach Goa.
Yes, I'm sure. Indeed. Thank you so much for the invitation. If at all possible, I will definitely come and visit. I don't know that it will be possible, but it is something that I would like very, very much. So I think very
Yes, sir.
fondly of Goa.
Surely we
So
would like to host you. Yeah. So you will see change in Goa as well, because what you referred was quite a long back. Okay, right from microwave to all the things, whatever in America, they are available in Goa now, inclusive of all the malls
I'm
and
sure.
everything. Okay, because yeah, because when you were
You know that I
explaining
had not
the
seen, I
concept
had,
of microwave, yeah, that was in long back.
yeah, you know,
Yeah.
I must tell you that before I left India for the United States, I had never watched a TV before. So, so it was,
Yes.
for me, big changes. So, yeah. So thank
Yes,
you so
yes,
much again.
surely. But yes, yes. Thanks